Okay, here we go. Good afternoon, everybody. Today, as you can see, we will be covering exponents. There have been, of course, uses of these already so far this course. We have been exposed to them, particularly in the geometry section, but here we're going to cover all of the rules of the exponents and how we use them. So, I'm going to deviate from the lecture notes just a little bit to start with. Just because I like to do this demonstration, it starts to make everything just a little bit more clear. Starting off with a very simple point, an exponent exists to show what happens when you're multiplying something by itself a certain number of times. So if I have this some number, we'll call it x, and in multiplying by itself 3 times, we use the exponent 3. Multiplying 3 times, we have the exponent 3. Starting with that piece of notation and just holding on to that idea, I'm going to show you a demonstration of what happens moving through different levels of powers or exponents, and it will help make the exponent laws that I'm about to go through a little bit more clear. I need a little bit more space. So what I'm going to do here is I'm just going to draw out what we're going to do with these numbers. Oops, already have 3's. Okay, so 3 times 3 times 3 times 3. No problem. That's 3 to the 4th. That's what we're expecting it to be. As we move down here, 3 times 3 times 3, we're dropping one exponent. Oops, try that again. And what I would like you to take note of in terms of what's happening as we move down this little ladder is at each level, I'm dividing by 3. So if I have 4 3's, and I divide by 3, then I'm down to 3 3's. And then I divide by 3 again, and I'm down to 2 3's. And then I divide by 3 again, and I'm down to 1 3. So that when we come down to ask ourselves now, what happens if I go down one more? Going from 3 to the power of 1 down to 3 to the power of 0, the exact same thing is still happening. We are dividing by 3. And it is worth noting that 3 divided by 3 is 1. And that's where we get the logic that anything raised to the power of 0 is going to be equal to 1. Following along this same logic, we can start to discover what happens when we go into negative exponents, right? So we're going down 1 every time here, go from 0 to negative 1. Well, I'm still dividing by 3, and in fact, we can show it directly. 1 divided by 3. Because once again, as we've gone down, we've simply divided by 3. And then that logic continues. If I wanted to find out what is 3 to the negative 2, well, again, we are dividing by 3. And our rules of fractions say when you divide by 3, you flip that second one and multiply. And so we end up with 1 over 3 squared, or 1 over 9. And it carries on all the way down. So that's sort of a quick demonstration of what's happening with our integer exponents going down, all of our whole numbers. We can see why we get to the 4 digits. We can see why we get to 0 because it's our base number divided by itself. We can see why we then get to negative numbers. It turns into a fraction because, again, we take our 1 divided by its base number, and all of a sudden our base is on the bottom of the fraction. So that's seeing it with real numbers. And now I'm going to flip back and start to follow exactly along the line with the lecture notes and we'll go through these exponent laws, but this gives you something to hang those exponent laws on to start with. So, in an exponential expression, like this one, A is called the base. So any number that's there at the bottom, that's called the base. And then this, of course, up here is called the exponent. Sometimes we also call it the power. And then we get into a bunch of laws that are based on this. So, as we just looked at, any number to the power of 0 is going to be 1, as long as your base itself is not actually 0. 0 to the power of 0 is not a defined number. You can't call it 1. So it's just worth noting that in all of these cases, we are not dealing with 0 as a number. The next law that we were looking at, what happens when we deal with negative numbers? Well, that tells us that we're dealing with this on the other side of the fraction line. Okay? You can put the 1 there as the exponent, but by convention, if it's to the power of 1, we don't write the exponent. It is worth noting here that no matter which side of the fraction line you're on, if your exponent is negative, you move to the other side of the fraction line. So if I had some number 1 over m to the power of negative 2, I could actually just rewrite that as m to the power of 2. The next part that I want to deal with in terms of negatives is taking note of where the negative falls in relation to your base. If you see something like this, you kind of want to break it out into all of its pieces. So the a squared part is the a times a, but that negative implies that we have a negative 1 out front of the whole thing, which is different than if I had some negative number in brackets, and then it would be all squared. So in that case, what I'd be getting is I'd be getting a negative a times a negative a, which actually would then come out to the positive version, because the negative times the negative is a positive. Moving along to interacting powers. If I have some number to the power of m, and I'm going to multiply that by some power of the same base, that's the important part, of the same base to the power of n, I can just end up adding these exponents. I'll give you a demonstration of that. If I have 2 to the power of 4, and I'm multiplying that by 2 to the power of 3, that's the same as saying 2 times 2 times 2 times 2. There's my first 4, times 2 times 2 times 2. There's my next 3. If I count those up, that's a total of 7, which is the same as saying 4 plus 3. So for the most part, we can actually just jump from there to there. Another quick example, without the middle part, if I had 4 to the power of 7 times 4 to the power of 6, that would be 4 to the power of 7 plus 6, or simply 13. In the same way that when we are multiplying numbers of the same base, we add the exponents. If we are dividing numbers of the same base, we subtract the exponents. So my same a to the m and a to the n, if I have a to the m divided by a to the n, that is going to be a to the power of m minus n. Using the same quick examples, if I had 2 to the power of 4 divided by 2 to the power of 3, That would be the same as saying 2 times 2 times 2 times 2 over 2 times 2 times 2. And as we've seen in previous things, we can cancel these top and bottom, which just leaves me with 1, 2 in the end here, which is the same as saying, oops, wrong color. Same as saying 2 to the power of 4 minus 3, which just gives us 2. Moving along, if we have some number raised to a power and that whole thing is raised to a power, we multiply the powers. Why do we multiply the powers? Yes, we multiply the powers. So we do that because if I have 2 to the power of 4 raised to the third power, that's going to be the same as saying 2 to the power of 4 times 2 to the power of 4 times 2 to the power of 4, which as we just learned is the same as saying 4 plus 4 plus 4. And instead of adding, we could just go 3 times 4, in this case, 12. So instead of having to write out all of those steps, if I had 4 to the power of 6 raised to the 7th power, that's just the same as saying 6 times 7 in terms of the powers. And I get 4 to the 42. To answer the question that just popped up, Lauren, yes, you're absolutely right. That's what it equals. Last thing to note in terms of the power rules that we're pulling out, if you've got multiple numbers being raised to some power, it's the same as raising each of those numbers to that power. You can distribute the power. So this also follows when you're dealing with negative exponents. If I had a over b all raised to the power of -2, for example, the negative now applies to both of these things. So we're going to change sides of the fraction sign for both of them, and then I can apply the power to both of them. Okay, so I've tried to give examples of these things as we've gone along. There are a couple of other examples, really quick examples in the lecture notes. I'm not going to go through those. I'm going to jump straight to the first worked example. So we are being asked to simplify. Three to the power of -2 times 2 to the power of 3 plus 5 to the power of 0, that's a 0, there we go, over 3 to the power of 3. Order of operations tells us the first thing that we do ahead of everything else is exponents. Where it goes brackets exponents, so we're going to do all the exponent work first. It's negative, so I know I'm going to be 1 over, and then 3 squared is 3 times 3, or simply 9. 2 to the power of 3 is 2 times 2 times 2, which is 8. 5 to the power of 0 is 1, and then 3 to the power of 3 is 27. From there, we can simply follow all of the things we're supposed to do. We need common denominators. That's what the fractions rules tell us. So 9 needs to match with 27. It's quite easy. We multiply it by 3. Whatever I do to the bottom, I must do to the top. And I end up with 3 over 27. 8 is not quite so easy. 8 does not deal with 27s nicely. So in the end, we have to multiply 8 times 27, top and bottom. And when we do that, we end up with, oh, sorry, I just realized I'm missing my own notation here. This is a multiplying. Sorry, before we do this, let me step back a moment. My apologies. This is still 1 over 9, but this is multiplying by 8 before we add. So I can multiply before we add 1/9 times 8, which is just 8 over 9. That'll make our job a little bit easier. We still have to multiply by 3, top and bottom, but now that takes our 8 into account, which makes our numbers much nicer. And we end up with 24 over 27 plus 1 over 27 for a final answer of 25 over 27. Okay, next worked example, unless there are other questions on that. Why not write 8 times 27 plus 1 times 9 over 1 times 27? I'm not sure I understand. Let me just write out what I think you're asking here, Lauren. So you're talking about, oh, you were talking about up here. Oh, at this stage here. I don't know that it necessarily would be easier. I think you get to the same place. If that makes more sense in your head, I would follow that.
Yeah.
Okay, I'm going to come back to that. I want to think about what you're asking there, and we'll come back around to that. Okay. Next question we're asked to simplify is negative 2 to the power of 4 plus the whole of negative 2 to the power of 4. I wanted to do this example really quickly just to reinforce the difference between these two things, something in brackets being raised to the power, something outside of brackets being raised to the power. 2 to the power of 4 is 16, so this first one becomes negative 16. Negative 2 to the power of 4 is also going to be 16, and because I have an even number of powers, my negatives are going to disappear. Those of you who are not quite seeing why my negative disappears there, I'm just going to do this over here. This becomes negative 2 times negative 2 times negative 2 times negative 2. With each pair, negative times a negative becomes a positive, so that becomes a positive 4. And the same thing happens here, a positive 4. And then my positive 4s multiply together, and I end up with my positive 16. So, having done that, negative 16 plus 16 and we end up with 0. Okay, simplifying expressions with exponent terms. Simplifying an expression containing exponential parts, we need to have as few exponential terms as possible. Usually this involves carrying out the operations that are in the expression. So we're trying to simplify it down as much as we can, and we want to have no terms with negative exponents. The reason why we want to have no terms with negative exponents has never been well explained to me. It largely has to do with convention over time. Just one of those things that people expect is that you're going to get rid of all of the negative exponents. So that's what we do when we simplify an expression. Again, we're being asked to simplify. And let's take 3 squared times a to the power of 3 times b squared, all to the power of 3. And this gets multiplied by 4 to the negative 3, a to the 3, b to the negative 8. And we get to assume that a and b are non-zero. So the first thing we want to do is we want to deal with our numbers. We want to turn those into whole numbers without exponents, because it's the easiest thing to do with both of them. 3 squared is 9. And I'm going to carry that a to the 3, b to the 2 with me for a second, and we're going to keep that cubed. 4 to the power of negative 3. 4 to the power of 3 is going to be 64, and it's a negative exponent, so I end up with 1 over 64. A to the 3, and b has a negative exponent on it too, so I end up with 1 over b to the 8th. Next thing I'm going to do is I'm going to apply this exponent outside the bracket. It has to share by each thing inside the brackets. So I end up with 9 cubed, a to the power of 3 times 3, which is 9. I'll do that a little bigger so it's a little easier to read. 9 cubed, a to the power of 9, b to the 3 times 2, which is b to the power of 6. And then nothing has changed here. I'm just going to clean it up a little bit. I'll get a cubed on top. I will have 64 and b to the 8th on the bottom. Now I can multiply these two sides together. While I do that, I'm going to take my 9 and I'm going to raise it to the 3rd power. And I end up with 729, a to the 9th, b to the 6th, times a cubed, and then on the bottom I still have my 64b to the 8. The only reason I've done this is so that you can see that I'm going to take my a's of they're the same base, so I can put those together and I end up with 729 a to the 12th, b to the 6th, over 64 b to the 8th. Now I can have my b's interact. This is going to be a subtraction, so 6 minus 8, which gets me to negative 2. We don't want negative exponents, so I'm going to leave it on the bottom. 729 a to the 12th over 64 b to the 2. Okay. Everyone's still with me? Okay, so just about half are in that stage of a little lost, but keep going, I'll catch up. So I'm just going to stop and clarify a couple of things on this question then to make life a little bit, hopefully a little bit easier. At this stage, I should point out that that goes with that, and they add. That's how we get the 12 there. Here, those subtract. And because it's a negative, we want it on the bottom of the fraction, so we put it there. Those are the two pieces I skipped over a little bit quickly, so hopefully that'll help clarify some things for some people. The 729 came from the 9 cubed, 9 times 9 times 9. Okay. Let's go on to another worked example. So again, we're going to simplify, and I have x to the power of negative 3 plus y to the power of negative 1 over x squared. So the very first thing we want to do is get rid of all of those negative exponents. So we're going to get everything on the right side of the fraction lines. First one becomes 1 over x cubed. The y wants to come to the other side of the fraction line, so we leave a 1 up top, and we end up with x squared y. Now we just have a pair of fraction questions we have to deal with. I need to get this side up to an x cubed, and I need to put a y on this side in order to make these balance. So what that's going to look like is this is going to multiply by x over x, and this side is going to multiply by y over y. And we end up with y over x cubed y plus x over x cubed y, which we can simply leave as y plus x over x cubed y. Why wouldn't it be x squared divided by y? Because there is no negative on this exponent. Because there's no negative on this exponent, it doesn't change where it is in the fraction line. Only the y has the negative, so it's the only part that moves. Does that make sense? Great. Any other immediate questions on this before I move on to fractional exponents? Excellent. Okay. Fractional exponents. I had it on my little pre-class picture, but I'll show it again. So if you have, well, we'll start with the notes. An exponent in the form of a fraction like 1 over n represents what we call the nth root of a number or of a base. The root is that number which, when raised to the nth power, gets you your original number back. That's a really fancy way of saying if I have 1 over n and I multiplied it by n, I'd end up with a power of 1. Okay, so if I had some number I'll do it the other way too. If I had some number x raised to the power of 1 over n, and I multiply and I raise that, to the power of n, ultimately I'd just end up with x. These would cancel each other out. Now, because we're dealing with the nth root of things, what we're ultimately dealing with are radicals. That's what that sign is. That is called a radical sign. And the reason it is called a radical sign is because of the word, what the word radical originally meant, which was to go back to the roots. So ultimately, we are again getting back to the root of something by using the radical. While I'm sitting here doing this and showing little things, when we have something like this, I have x to the power of 1 over n. I'm looking for the nth root of x. When I move that, I can throw that into a radical. Whatever that number on the bottom is goes in that little check mark part to show us which root we're dealing with. And the x goes there, and then whatever number is on the top part of the fraction remains the power on the base. Then we go through a bunch of examples with this stuff in sort of a whole bunch of different forms, and then I'll show you what we can do in terms of working problems with it. So we start off with a fairly straightforward example. If I have 49 to the power of 1/2, it's the same as saying I would like the square root of 49. It's worth noting you don't often see the 2 that goes on in here. It's implied. If you don't see it, you assume that there is a 2 there. That's what we mean by the square root. And that gets us to 7. And the reason for that, of course, is because 7 squared gets us back to 49. So you can see that 2 1/2 relationship. If I had 8 to the 1/3, this would say that I'm looking for the cubed root of 8, which is 2. And that is true, I know, because 2 to the power of 3 gets me 8 back. So when we're dealing with fractional exponents with 2 numbers larger than 1 on top and bottom, an exponent like m over n can be thought of as taking the nth root to the mth power. And you could also go the other ways around. You could take the mth power first and then take the nth root. You end up with the same result either way. I'll show you. I'm going to do it both ways so you can see it. So let's say we have 4 to the power of 3 over 2. What this is essentially saying in one form is that I want the square root of 4 raised to the 3rd power. So I'll do this part inside brackets first. The square root of 4 is 2. And then that gets raised to the 3rd power. And as we saw earlier, 2 to the 3rd power is 8. I can do the exact same question, but this way I can do it. I want to take the square root of 4 to the 3rd power. 4 to the 3rd power is 64, and the square root of 64 is 8. So you can see it really doesn't matter which way you go with it. It works out the exact same way both times. Now, it is worth noting that when we're dealing with fractional exponents, those exponents that are fractions are still fractions, and they behave like fractions. Sorry, that should be 3 over 2. Three on top, 2 on the bottom. When we're dealing with fractional exponents, the fractions in the exponents are still fractions. So if I have 4 to the power of 3 over 6, well, 3 over 6 reduces. So I can go ahead and just reduce that fraction down to 1/2. Which, as we learned just now, is the same as asking for the square root. So we just take it, and we're good. Okay, a worked example. Nine to the power of negative 1/2 plus 2 to the power of 4 over 2 minus 3 to the power of negative 2. Nine to the power of negative 1/2. There's a couple of things happening in there at the same time. We have the negative, which is telling us to put it on the other side of the fraction, and then we have the 1/2, which is asking us for the square root. So, because of the negative, the first thing I'm going to do is 1 over, and then I will take the square root of 9. And there's my 3. The next thing we want to do is we come over here. We have 2 to the power of 4 over 2. Well, 2 goes into 4 nicely, so this can actually just reduce down to 2. So 2 squared is 4. And then again, we have this negative part that we want to deal with. This tells us we're going to put it on the other side of the fraction, and then we're going to square it. So I end up with 1 over 9. And now I want everything with the same denominator. The lowest common denominator for all of these is going to be 9. So this will multiply by 3. We'll treat that as over 1, and it will multiply by 9. When we do that, I end up with 3 over 9 plus 36 over 9 minus 1 over 9. Bottom stays the same because we're adding and subtracting. 3 plus 36 gets us 39, minus 1 gets us down to 38. So far, so good, fairly simple and straightforward. However, when we get into some of the more complicated things, like I'm about to throw up right now, we want to make sure that we're keeping track of all of our pieces. So I'm going to try and take as much room for this as possible. And when you guys are doing your work, I suggest you also take as much room as possible. Most mistakes happen just because we're trying to rush through the steps. So we are being given, all in brackets, 27, a to the power of 6, b to the power of negative 7, c squared, all over 3, a to the power of negative 2, the letter b, and then c to the power of 4, and the whole thing is being raised to the power of 1/2. For myself, I find it easiest to do everything inside the brackets before trying to apply that external exponent. So what's going to happen is I'm going to work on the inside, and this 1/2 is just going to carry down until we're ready to use it. So what can I do to make my life easy to begin with? I'm going to simplify top and bottom. 3 goes into 27 9 times. A to the 6th over a to the -2, that becomes a subtraction question. I'm going to write it out really explicitly just so that we can keep track of everything. So this becomes 6 minus -2. I know it's a weird way to write out the powers, but I want you to see what's happening clearly here. I'm going to get a to the power of 6 minus the -2 from the other a. So a to the power of 6 minus -2. I'm going to do the same thing with my b's. I'm going to keep it all up. Oh, that's a bit tall. All up top for the time being. I'm going to get b to the -7 minus 1. Just to be clear, that 1 comes from the implied exponent on the b. And then finally, I'm going to take c to the power of 2 minus 4. And now I have nothing left on the bottom, so we're fine, and that 1/2 comes for the ride. Now we can simplify everything inside here. The 9 stays as it is. 6 minus -2 is the same as saying 6 plus 2, so we end up with a to the power of 8. -7 minus 1 becomes b to the -8. 2 minus 4 gets us -2. This is all still in brackets and all still raised to the power of 1/2. Now I'm going to apply this exponent. Remember, it shares with each thing in here. So we have to use that 1/2 4 times in this case. When we do that, I end up with 9 to the power of 1/2. I end up with a to the power of -8 over 2. I end up with b to the power of, a is a positive 8 over 2. B is a -8 over 2. And then c is simply -2 over 2. Nine to the 1/2 is the same as asking for the square root of 9, so it becomes 3. A to the power of 8 over 2, 2 goes into 8 4 times, so we have a to the power of 4. The negative tells us we want it on the other side of the fraction line, so the b is going to come down, and again 2 goes into 8 4 times, so I have b to the power of 4. C is negative, so it too comes to the bottom of the fraction, and 2 over 2 is to the power of 1, so we don't need to write anything, and we can finish off there. Any questions on how we got to the finish of that question? Excellent. Okay, so now that we've been introduced to fractional exponents, and we can now move on to start dealing with radicals and radicals.